Hi, today we're going to be talking about something very special in chemistry, moles. All right. And the basic concept of dealing with moles is in chemistry, as you know, we deal with very, very, very small particles. All right. And in order to have enough small particles that we can actually manipulate them and deal with them in the real world, we need to group them together in large quantities, extremely large quantities. And that, dear children, is where we get the concept of moles. You see, atoms, individual atoms, have very, very tiny masses, okay? And I mean, we're talking incredibly small. Just to give you guys a brief idea of how small an atom really is, if you were to consider, imagine the atoms in the eyeball of a mouse, okay? Think of how small a little eyeball of a little mouse is. The atoms that make up that eyeball are roughly the same scale size-wise as that eyeball compared to the overall world, to the overall Earth, okay? So atom is to eyeball as eyeball is to the Earth, just to give you guys a sense of scale. And since they are so small, measuring them in grams is actually completely useless, really, okay? Therefore, chemists have devised a unit specifically for individual atoms, and that is known as the Unified Atomic Mass Unit, or just U for the symbol, okay? Or for the unit. And it is approximately 1.66 times 10 to the negative 24th. Sorry. Oh, dog is saying hi. This is Murray. So 1.66 times 10 to the negative 24th grams. Now, just so you know, that is the mass of a single proton or neutron. So if you're trying to figure out the mass of an individual atom and it has, let's say, 6 protons and 8 neutrons, you just add them up. 6 plus 8 is 14, and you would say that individual atom has a mass of 14 U's, okay? Or unified atomic mass unit. Now, so they're measured, this is what the mass numbers are. So when you have like carbon 14, the C14, that's what it's talking about, okay? Now, atomic mass, this is what we actually see written out on the periodic table, all right? The atomic mass is different, okay? Atomic mass is the weighted average of the masses of all the different isotopes of an element, all right? Now, as you guys know, different atoms or different elements can have different number of neutrons and therefore different mass numbers. All right. Once again, carbon, for example, carbon has several different isotopes. That's when you have the same element but with different number of neutrons and therefore masses. For example, one is carbon 12. It has 6 protons and 6 neutrons for a grand total of 12 U's. But there's also something like carbon 14. Carbon 14 has 6 protons and 8 neutrons. Now, it's still carbon because it has 6 protons. That's what defines what an element is the number of protons. So you would say that it has a mass of 14 and its number, C, or carbon 14, indicates that mass. Well, when you look on the periodic table, all right, the number that you look on there for carbon is not either 12 or 14. It's actually like 12.011. All right. And it's a fraction. All right. It's a decimal. And the reason why is because it takes into account the masses of the different isotopes in an element and the relative abundances, how common they are. Okay. And this is why atomic masses are not whole numbers. Now, you could, for ease sake, maybe round them off to a whole number, but that's not what we do in here, okay? So basically what you need to do when reading atomic masses off of the periodic table, always go to 2 places past the decimal place, okay? Always go to 2 places past the decimal, so that carbon, instead of 12.011, you go to 12.01 when you read it, all right? So you have the number, decimal, and then 2 more places. You round off after that second place, all right? So for example, hydrogen on the periodic table says it has a mass of 1.008, but you should read it as 1.01 U's. Okay. Now, by the way, real fast, why is it? For example, carbon 12 is carbon is 12.01. Well, yes, it takes into account the fact that there's carbon 12 atoms and carbon 14 atoms, but it's carbon 12 is by far the most common isotope of carbon. That's why it kind of skews the average much closer to 12. Yes, there's a few carbon 14s and carbon 13s, even some carbon 11s. But when you look at all of them, there are by far more carbon 12s, and that's why the mass, the atomic mass, is 12.01. Okay? Now, as I was saying, since atoms are so incredibly small individually, we need to have enough of them that we can actually deal with them. I mean, if you're a chemist and you want to react some hydrogen with oxygen, you're not going to take a hydrogen molecule and an oxygen molecule and kind of cram them together or anything. It doesn't work that way. You need to have a large enough amount that you can actually deal with them in the real world. And that's where the mole comes into it. Now, the mole is defined as the number equal to the number of carbon 12 atoms in exactly 12 grams of pure carbon 12. We'll get to that in a minute, okay? We'll get to what that really means. But basically, the mole is a really large number, all right? It's a very large number. Large enough so that you have enough atoms that you can actually deal with them in the real world, okay? Like the term dozen, it represents a specific number of things. Now, it is used to represent many small atomic-sized representative particles. Now, the term representative particles is like the smallest size something can take, a unit, smallest unit in which a substance naturally exists in. So if it is something like helium, helium is found in atoms. However, hydrogen, since they're diatomic, those smallest ones are molecules. It could be in individual ions, like oxide ions, O-2. That could be found in ions, or it can be what are known as formula units. If you're dealing with something like an ionic compound, like salt, those lowest, smallest units are formula units, but they're all representative particles. And you would, 1 mole is basically a large number of those. Well, how large? Really flippin' large. 1 mole of anything contains 6.022 times 10 to the 23rd units of that substance, okay? That is a really big number. Basically, imagine a 6, a 0, 2, 2, and then 20 zeros after it. All right? So you need that many of them in order to get enough that you actually can deal with and see in the real world. So a dozen is 12. A mole is 6.022 times 10 to the 23rd. Now, that is known as Avogadro's number or Avogadro's constant. And he was an Italian scientist that figured out this number. And you're going, well, wait a second. What's so special about that number? Why does it have to be that specific number? I mean, theoretically, what if you had 1 times 10 to the 24th? Wouldn't you have enough atoms to be able to see them and work with them? Yeah. But the beauty of this number is if you have exactly that number of U's, all right, of, let's say, protons or neutrons or anything that weighs one unified atomic mass unit, if you have 1 mole of those, then it would weigh exactly 12 grams. You see, it is the conversion that we use to go from the realm of AMUs, of U's. All right, sometimes they're called AMUs. And it goes from that realm to things that are measured in grams. So whatever it weighs in U's individually, whatever the atom or molecule weighs individually in U's, that's what it's going to weigh. If you have a mole of them, that's what it's going to weigh in grams. Okay? That's why the definition of this, it was set by saying, all right, if you have 12 grams of carbon-12 atoms, all right, if you have exactly 12 grams of carbon-12 atoms, that's how many a mole is going to have. Whatever number of atoms make 12 grams, that's how many is going to be 1 mole. And it turned out, after many painstaking measurements, he figured out that it was equal to 6.022 times 10 to the 23rd. All right, so a sample of an element with a mass equal to that element's average atomic mass, expressed in grams, contains 1 mole of atoms. And by the way, when you use moles as a unit, just use MOL. I know it doesn't save a whole lot, but that way it's kind of like the word deer. All right, you can say 3 moles and just write 3 MOL. And you don't have to worry about an ES or anything like that. It works for singular and for plural. And just to give you guys an idea, if you look at 1 mole of any of these items, these are their masses in grams. All right. Well, if you look on the periodic table, this is what the mass, the atomic mass of aluminum is, or this is the atomic mass of gold. All right. That's what all of these are equal to. And it makes it so much easier. So individually, a gold atom weighs 196.97 unified mass units, but a mole of gold atoms weighs 196.97 grams. Now, what we're going to do is we're going to use Avogadro's constant as an equality, all right? Just like we did with the unit analysis for metric conversions, now we're going to use it as an equality to convert between the number of particles, all right, number of atoms or molecules, to convert between that of a substance to the number of moles and vice versa. All right, and that's what I'm going to show you next. The sample question that we have is, how many copper atoms are there in 2.4 moles of copper? Now, first of all, we have to, as always, write down our starting point and end point. The starting point is the number, unit, and identity given to you in the problem. So 2.4 moles of copper. And the question is, how many atoms, which is a type of particle, of copper are there? Now, next we have to write out our equalities. Now, in order to figure out the equalities, we utilize our chemical conversion map. And since our starting point is in moles, our end point is a type of particle, and we're going from mole island to particle island, the bridge that we use is Avogadro's constant, which reads 1 mole of a substance is equal to 6.022 times 10 to the 23rd particles. Now we have to specialize and specify for this particular problem. So we say that 1 mole of copper is equal to 6.022 times 10 to the 23rd. And instead of particles, we utilize atoms of copper. Now, since this gets us to our starting point and only 1 bridge is needed, we only therefore need 1 equality. We set up our grid. We have 2.4 moles of copper in the top left-hand cell. Moles of copper are here, so therefore we need moles of copper down there. Therefore we put 1 mole of copper on the bottom, and 6.022 times 10 to the 23rd atoms of copper goes on top. Moles of copper cancel out. We're left with just atoms of copper, which is exactly where we want to end up. Now we use our handy-dandy calculator, and we go, since it's on top, we simply go 2.4 times 6.022 EE23 equals. And rounding it off to the correct number of significant figures, which in this case is 2, since there are 2 significant figures in the starting point, our answer is 1.4 times 10 to the 24th atoms of copper. Now, let's say we want to go the other way, and we have a question like, how many moles of iron are there in 4.8 times 10 to the 27th atoms of iron? So in this case, our starting point is 4.8 times 10 to the 27th atoms of iron. And the question is, how many moles of iron are there? Again, we utilize our chemical conversion map. This time we're starting off on particle island and going to moles. But again, we use the same bridge, which is Avogadro's constant. But we have to specify for this particular problem. So instead of 1 mole of copper, I say 1 mole of iron is equal to 6.022 times 10 to the 23rd atoms of iron. Notice how it's exactly the same number. Only thing that's changed is the identity of these substance. So I set up our grid again, since we only had one bridge. I have 4.8 times 10 to the 27th atoms of iron in the top left-hand cell. This time, since we have atoms of iron on top, we want to have atoms of iron on the bottom. So we use this right here. We put Avogadro's number of atoms of iron on the bottom and 1 mole of iron on top. When we use our calculator, well, first of all, cancel out atoms of iron, leaves us with moles of iron, which is exactly where we want to end up. This time, when we use our calculator, instead of multiplying, since it's on the bottom, we're going to divide. And we have 4.8 EE27 divided by 6.022 EE23 equals. And I get 7,970. Again, we only want 2 significant figures. That 7 changes the 9 into a 10, which changes the 7 into an 8. So my answer is 8.0 times 10 to the 3rd. All right, because the exponent's greater than 2, it has to be in scientific notation. Times 10 to the 3rd moles of iron. And there's my answer. I hope you found this helpful. Thank you.